So again here we have another question. It has been asked to find the Norton equivalent circuit across the terminals A and B for this circuit. So we'll be using Thevenin theorem method to find the Norton equivalent circuit. Okay, so first for Thevenin method we have to find VTH, the open circuit voltage across terminal A and B. So okay, we have this is 20 ohm, this is 30 volt, this is 10 ohm, volt. This is VTH. Let the circuit current be I. So the circuit current I will be 30 minus 20I, we are applying KVL in the whole circuit, minus 10I minus 18 is equal to 0. Okay, that implies 30 minus 18 is 12. 12 is equal to 30I, or that implies I is equal to 12 by 30 ampere. So I is equal to 12 by 30 ampere. So dividing by 3, it will be 4 by 10, which is equal to 0.4 ampere. So we have got I. So if we apply KVL from this point up to this point, the terminals, the two terminals, then we can get the value of VTH, that is 30 minus 20 into I, that is 0.4 minus VTH is equal to 0. That implies VTH is equal to 30 minus 20 into 0.4, which is 30 minus 8, which is equal to 22 volt. So VTH is equal to 22 volt. Okay, we have got VTH. Now we have to find RTH. So RTH is basically deactivating the independent sources. So here we have two independent voltage sources, so we have to short circuit them and find the equivalent resistance across the terminal A and B. So that will be 20. This is short circuited, this again, this is short circuited, 18 volt. This is 20 ohm and 10 ohm across A and B. So 20 ohm and 10 ohm are in parallel connection. So RTH will be 10 parallel 20, that is 10 into 20 by 10 plus 20, that is 200 by 30 ohm, which is around, let's say it is coming 6.67 ohm. That is RTH. So we have got RTH and we have VTH. So we have got the Thevenin equivalent circuit. So now we can get the Norton circuit. So the Thevenin circuit is this. This is 22 volt and this is 6.67 ohm. The Norton circuit will simply be applying source transformation. So for that, IN will be VTH by RTH is equal to 22 by 6.67, 22 volt by 6.67 ohms, which is coming around 3.3 ampere. So the Norton circuit will be 3.3 ampere, and the same resistor connected in parallel, the equivalent resistance 6.67 ohm. So here we have got the Norton equivalent circuit from the Thevenin equivalent circuit. Okay. Hello friends, so this is the third question related to Thevenin to Norton and Norton to Thevenin conversion. So here we have this circuit and we have to find the Norton equivalent circuit. So we'll find it from Thevenin circuit. So first we have to find the Thevenin circuit, and the first part is finding VTH, Thevenin voltage, the open circuit voltage. So for that we have to redraw the circuit. So here we have this resistor connected in this way and the 12 volt independent voltage source. So we'll redraw the circuit. See, here this 12 volt is connected, and across in parallel 10 ohm resistor is connected. So the voltage across this 10 ohm will also be 12 volt. So what I'm trying to say is that when you have a resistor connected in parallel across a voltage source, we can replace this with only the voltage source, because the voltage across the two ends of the resistor will be the same, V. So the resistor are connected in parallel across the voltage source becomes a redundant element, it is of no use. Similarly, if we have a resistor connected in series with a current source, then it is the same as the current source only, because the same current will flow through the resistor. So this becomes a redundant element. So always remember, a resistor connected in parallel across a voltage source and a resistor connected in series with a current source is of no use. Okay, always remember that. Okay, so here we can replace this whole circuit with this 12 volt, 10 ohm, 10 ohm, 10 ohm, A, B, 12 volt, 10 ohm, 10 ohm, and this. So we have to find this voltage, VTH. So VTH is simply applying voltage division rule. It's 12 into the voltage drop across this 10 ohm resistor, 10 plus 20. Okay, this. So here it is 12 into 10 by 30, which is 4 volt. Okay, 4 volt. Okay, 10 ohm, 10 ohm, 10 ohm are in series together. So we can consider these two 10 ohms as a single resistor of 20 ohm. So it will be a 20 ohm and a 10 ohm. So you get the point, and we have this 12 volt connected across it. Okay, we have combined these two 10 ohm resistors as they are in series to form one 20 ohm resistor, and the voltage division rule will be applied to find the voltage drop across this 10 ohm. So we have got 4 volt as the Thevenin voltage, the open circuit voltage. So VTH is 4 volt. Now we have to find RTH. So for that, what we'll do, we will short circuit this independent voltage source, and now RTH. Here again, as I said, these two 10 ohms will be in series. They will form a 20 ohm resistor, a single 20 ohm resistor, which will be in parallel with this 10 ohm resistor. So it is basically 10 plus 10, these two 10 ohm resistors parallel. The resultant is parallel with this 10 ohm resistor. So it is 20 parallel 10, which is 20 into 10 by 20 plus 10, which is 30, 200 by 30, which is coming around 6.67 ohm. Okay, 6.67 ohm. So RTH is 6.67 ohm. So we have got VTH and RTH. Now we'll draw the Thevenin circuit, and then from that we'll get the Norton circuit. Okay, so we have the Thevenin circuit, 7 ohm, this is 4 volt. B. Now Norton circuit, the Norton current will be VTH by RTH, which is equal to 4 by 6.67, which is around 4 by 6.67 is 0.6, nearly close to 0. It is 0.5 something, which is 0.6 ampere approximately. The Norton circuit is 0.6 ampere, and the same resistor 6.67 will be connected in parallel across it, 6.67 ohm. So this is the Thevenin circuit, this is the Norton circuit. Okay, so we have got the Norton equivalent circuit from the Thevenin circuit.